Absorption spectroscopy and flame emission spectroscopy. Flame emission spectroscopy sometimes is also called as flame photometry. We will first start with atomic absorption spectroscopy. As the name is suggesting, it is concerned with atoms and not with molecules. It is a spectroscopy in which absorption of electromagnetic radiation that takes place, and the absorption depends on how much of the atoms are present of the specific type. Different types of wavelengths will be absorbed by different types of atoms. So in a way it will be characteristic. So what we are going to measure in spectroscopy, which wavelength is being absorbed and how much is that wavelength has absorbed. So qualitative or quantitative analysis is done in this manner. So it is very sensitive method of extent of quantitative elemental analysis. Elemental analysis is extremely tricky part because matter is present in the form of molecules and not in terms of elements themselves. So it is very sensitive method. Then it is detection of trace metals in solution. Now when we say something is present in trace quantity, it means it is present in very small quantity. Because this method is sensitive, it is used for detection of trace metals in solution. It is independent of molecular form of metal. Whatever may be the molecular form, it may be a complex, it may be salt, it may be organic compound, whatever it may be, it has the capability to detect that metal in the sample. For atomic absorption spectroscopy, almost 60 to 70 elements out of your periodic table of elements can be determined in very low concentration in micrograms per ml, including rare earth metals, which includes cerium, dysprosium. See, these all names, I don't know whether you have heard it or not. The reason you did not hear them because they are present in trace amounts in nature. They are very scarce. All metals, this is done by direct method. That means the metal is detected directly. If you want to analyze copper, you are going to detect copper. Some metalloids by indirect method. Now, indirect method, you understand what is indirect method. Indirect titration में हम क्या करते थे? In the analyte, we will add excess of material which you can determine. Similarly, okay, some metalloids, some non-metals like selenium and tellurium. Disadvantages of this method is detection of one element at a time is possible. You cannot detect multiple elements simultaneously. The limitation is related to detector. Okay, which wavelength that is being detected by the detector has to be selected. Different source and different wavelength for different elements. This is what I was talking about. You need to change device depending on device parts depending on which metal you are going to detect. Limited use in qualitative analysis. If you don't know what you are looking for in the sample, it will be extremely difficult to determine which metal is present in the sample. But it has some applications in qualitative analysis also. Now let us see the principle. Observe this diagram. Electromagnetic radiation source, high density hot matter. It may be light bulb, it may be some star like our sun. If the electromagnetic radiation coming from it passes through diffraction gratings, it will give you one continuous spectra. Now instead of the dense material, if you heat a gas, that gas when radiates electromagnetic radiation and it passes through diffraction gratings, it will give you line spectra. It will be emission spectra in which few of the wavelengths are present. Rest everything is black background. Now if you take the same gas, if you cool it down, okay, it may be at room temperature, and this electromagnetic radiation you pass through it. The original electromagnetic radiation after passing through grating gave you continuous spectra. But when it passes through the gas before, the exact wavelengths which were present in emission spectra will be absent in the absorption spectra. So this third kind of scenario we are going to use in atomic absorption spectroscopy. We will create a cloud of gas consisting of atoms, and we will pass electromagnetic radiation through it. The gas will absorb some of the wavelengths which is characteristic of that gas, and you will get the characteristic spectra. When a sample containing metallic atom is heated about 2000 degrees Celsius, it first undergoes partial or complete dissociation, then volatilizes to free gaseous atoms. So basically what we are doing, we are converting the metallic atom into gaseous atom. Okay, we are converting it to gaseous atoms. Now, the electrons of the gaseous atom exist in discrete quantized levels. That means it has got orbitals. They are in orbitals which have specific energy levels that are of the element. So energy levels of copper will be different from silver, which will be different from iron, and so on. This is not only true for metals, it is true for every element. The electrons in the outer orbitals of the atoms may absorb thermal energy and be promoted to one or more higher energy levels. So the electrons in the outermost orbit are capable of absorbing the energy from surrounding. It may be in the form of heat, it may be form of electromagnetic radiation, it may be vibrational energy. So all the forms it can absorb and get itself promoted to higher energy state. But larger percentage of the metal atoms will remain in the ground state. We have seen this in IR also. Most of the atoms, most of the molecules, they try to remain in the ground state. When a light of resonance wavelength is passed through the flame having metal atoms, part of the light will be absorbed. If electromagnetic radiation passes through that cloud of atoms, and if the energy of the electromagnetic radiation matches with the energy difference between two different levels, energy levels of the electrons in the outermost orbital, it will absorb, that electron will absorb that energy and get excited to the higher energy level. The absorption of light is proportional to the concentration of the metallic elements present in the flame. More elements are present, more atoms are present, more intense absorption will take place. Once the value of absorption is known, the concentration of the metallic element can be known or can be calculated. Mathematically, the total amount of light absorbed is given by this particular formula. At frequency nu, the total amount of light absorbed is equal to pi e square divided by mc multiplied by n multiplied by f. Now, where this E is charge on electron, this is charge on electron, pi is constant, m is mass of that electron, c is speed of light, capital N is number of atoms that can absorb the frequency nu in the light path, and f is oscillator strength, or what is being oscillated here, the atom is getting oscillated, it is vibrating. So ability of each atom to absorb that electromagnetic radiation. So if you will observe, pi is a constant value, charge on electron is constant value, mass of any electron is a constant value, this c, speed of light, it is also constant value. So it is being changed in molecule, these two factors, n and f. So as pi e m c are constant, then the simplified equation becomes total amount of light absorbed of frequency nu is equal to constant multiplied by n multiplied by f, where n is the number of atoms that can absorb frequency nu. This nu is mentioned over here. Frequency nu in the light path, and f is oscillator strength or ability of each atom absorb that electromagnetic radiation. If the temperature is low, Okay, if the temperature is low, you can imagine what will happen to the atoms and Terra energies. Not all analyte in the sample solution will be evaporated. It will be difficult to evaporate the atoms. It will affect the number of species of analyte present in the flame. Obviously, there will be less number of atoms present in the flame that will absorb. So, there is a loss of signal. If temperature is too high, metal, particularly alkali metals, are converted to ions. That means they easily lose electrons. And ions do not absorb electromagnetic radiation because the electrons that was responsible for the excitation is lost. So the inner electrons, they are high energy electrons. It is difficult to excite them. So it affects the number of species of analyte present in the flame. As a result, there is loss of signal. Okay, this is one of the example of line spectra. It is of sodium. Now that was the principle of atomic absorption spectroscopy. Now let us consider principle of flame photometry. Now the flame photometry is also named as flame emission spectroscopy (FES) because of the use of flame to provide energy to the excitation of the atoms. When metallic salt solution introduced into flame, the atom absorbs thermal energy and get excited. Now when we talk about, just linger around the second point, when we talk about salts, it is the complete exchange of electrons between the cation and anion. What happens is if you introduce such salt in flame, the salt molecules, they absorb that thermal energy, and as an atom, both cation and anion get excited to higher energy state. Heat of flame can cause excitation of an electron from ground state to higher energy state. This is very much obvious that atoms, that is specifically the electrons, can absorb the energy from the flame. But excited atom has very short lifespan, 10 raised to minus 9 seconds, and its return to ground state is accompanied by emission of radiation. So when that high energy electron comes to ground state, it emits photon. The following processes are involved in the flame photometry. First, the solvent is vaporized, leaving particles of the salt. Suppose you are taking solution of sodium chloride. So the moment a fine mist or fine spray of sodium chloride solution is introduced into the flame, the first thing that will happen is the water in which NaCl is dissolved will get evaporated. Second, that is converted into gaseous state. The sodium chloride, which is normally in solid form, because of heat, it will be converted into gaseous sodium chloride vapors. The gaseous molecule is dissociated into gaseous atoms or radicals. So NaCl, there are two possibilities. It may form Na plus and Cl minus, or if it has got sufficient energy, it may form metallic sodium and atomic chlorine. The atoms are excited by thermal energy of the flame. So the energy is acquired in the form of thermal energy. The excited atoms are unstable, quickly emits the photon and return to the ground state. The atoms which are now in higher energy state, they will come to ground state by emitting the photon. Measurement of the emitted radiation forms the basis of flame photometry. I will give you people time of say 30 seconds to 1 minute to just go through these sequence. Let us consider the energy differences of the electronic energy levels within the atoms, what must be happening with it. Let us consider that if E1 and E2 represents the energy of lower and higher energy levels, that is, this is E1 and this is E2. These are two energy levels for electron. The radiant energy emitted during the transition from E2 to E1. Okay, so there is electromagnetic radiation emitted here, the energy difference between two of the energy level will be equal to h nu. Now nu is equal to c by lambda. Okay, nu is frequency, it is equal to c by lambda. So lambda is combined, lambda is equal to, we can derive here, let's put lambda on left hand side and bring E2 minus E1 in the denominator on the right hand side. So we get lambda is equal to Hc divided by E2 minus E1. From this equation, one can calculate the wavelength of the emitted radiation, which is characteristic of the atom of the participating particular element. Now, if you change the element, lambda will be different for different wavelength. The wavelength lambda tells about the type of element present in the flame. The intensity of the emitted light is enabled to know the amount of element present in that flame. If, say, suppose sodium is present in large amount, you will get bright yellow electromagnetic radiation coming from the flame. If there is potassium present, there will be slight orange color to the flame, and the more potassium present, the orange color intensity will go on increasing. Now, let us compare atomic absorption spectroscopy and flame emission spectroscopy. First column is distinguishing point, then we have flame photometry, and then atomic absorption spectroscopy. The first is generation of the signal. What is origin of the signal? What is phenomena behind the signal? So in terms of flame emission spectroscopy, atoms excited due to the high temperature of the flame, and when they come down, they come to ground state, they emit characteristic photon. These photons are signal. The photons that are emitted are the signal. In atomic absorption spectroscopy, on the other hand, the fraction electromagnetic radiation coming from the source is absorbed by the atoms in ground state present in the flame. So in this, the analyte is not creating electromagnetic radiation, it is simply absorbing electromagnetic radiation, which is its characteristic. The decrease in the electromagnetic radiation intensity is the signal. Now, effect of temperature. What will happen to increase or decrease in the temperature? Signal is influenced by the temperature. Signal is not influenced by the temperature in atomic absorption spectroscopy, provided the you can say provided the temperature is not too low so that atoms are not formed. Okay, anyway, the linear relationship between absorption and concentration, BS law is not obeyed, but here BS law is obeyed because it is absorption spectroscopy, so BS law is obeyed. Now, what are advantages of atomic absorption spectroscopy over flame emission spectroscopy? Atomic absorption spectroscopy is as compared to be more specific. Elements absorb own characteristic wavelength. It does not suffer from spectral interference which occurs in flame emission spectroscopy. Now, I will explain this. In flame emission spectroscopy, the oxidation is being happened. Okay, there is oxidation happening, and you will require fuel. You will require fuel for the flame, and in that fuel you are mixing your analyte. So analyte plus fuel plus oxygen gives the flame. What if the oxidation of fuel, which is generating the majority of the flame, those electromagnetic radiation are interfering with the electromagnetic radiation coming from the analyte? So you will get wrong reading. This will not happen in atomic absorption spectroscopy. Another advantage, atomic absorption spectroscopy, large number of atoms in flame at ground state are responsible for signal, and in case of flame photometry, small number of atoms in the flame at excited state are responsible for the signal. Therefore, atomic absorption spectroscopy is unaffected by the temperature. In the second point, in this particular point, the basics of atomic absorption spectroscopy and FES comes in picture. See, we saw that at any given point of time, at any circumstances, most of the molecules, most of the atoms, they will try to remain at ground state. So atomic absorption spectroscopy deals with atoms in the ground state. In case of flame emission spectroscopy, the atoms which are already at the excited state, they are responsible for the signal. But by law of thermodynamics, most of the atoms will try to remain in ground state. So small fluctuation in the temperature will cause significant change in the quantity of atoms which are present in high energy state, which are responsible for giving out signal. Third, by atomic absorption technique, traces of one element can be determined in presence of high concentration of other elements. This will not be possible in case of FES because of high interference. There are disadvantages to atomic absorption spectroscopy also. This technique has not proved very successful in the estimation of elements like vanadium, silicon, molybdenum, titanium, aluminium, because these elements give oxides in the flame. In aqueous solution, the anion affects the signal to a noticeable degree. So there is formation of ions. Separate lamp is needed for determination of each element, so it is kind of disadvantage. Attempts are being made to overcome this difficulty by using continuous source coupled with monochromator, but it is very difficult to get monochromator which produces consistently single wavelength and not small band of wavelength. Moving on to the next point. Okay, so analysis of liquids. First step is desolvation, drying. Next is vaporization. The solid sample is converted to gaseous sample, and then it is atomization. That molecular gas is broken down into atomic gas. Now, this is the basis both in atomic absorption spectroscopy and in atomic emission spectroscopy.